In the age of infinite information, the strangest thing you can find is an empty space. A line in a record that should contain detail, names, dates, memos, attachments, and instead contains nothing you're allowed to see. Out beyond the reach of the naked eye, a faint visitor crosses our neighborhood on a path that does not loop back. Its orbit does not belong to the sun. And on paper, the story sounds almost boring. NASA lists 3 Atlas as a comet: natural, active, dusty, passing through on an interstellar trajectory, posing no threat to Earth. But the tension begins the moment you step away from telescopes and into the language of institutions. A Freedom of Information Act request asked the CIA whether it held records about 3I Atlas. The response, reported publicly, was the phrase that always feels heavier than it is. The agency could neither confirm nor deny the existence of records. A sentence like that can be procedural, an old legal reflex meant to protect sources and methods. But to an audience trained by decades of hidden folders and redacted lines, it lands like a shadow cast across a simple comment. So we need one calm rule before we go any further. Bureaucracy is not a telescope. It can shape emotion, but it does not change an orbit. The only way to keep our footing here is to follow measurable astronomy first, and treat every interpretation as secondary. Start with scale, because scale is how the sky resists our storytelling. NASA's public numbers are plain. 3I Atlas stays far away. Its closest approach to Earth is about 1.8 astronomical units, roughly 270 million kilometers. Its closest approach to the Sun is around October 30, 2025, at about 1.4, about 210 million kilometers, just inside the orbit of Mars. If you want to feel those distances instead of just hearing them, remember this: 1 astronomical unit is the average Earth-Sun distance. So 3I Atlas never even comes as close to the Sun as Earth does, and it never comes anywhere near our doorstep. And yet, distance does not remove mystery. In some ways, distance creates it. When an object is faint and fast, early measurements arrive like scattered raindrops. Each observation is a small stamp, a few pixels of light, a timestamp, a sky coordinate. The orbit you compute in the first days is not a verdict, it is a draft. In drafts, uncertainty can look like deviation. Noise can look like intention. And the most dangerous word early on is changed, because what has changed is often not the object, but our estimate of where it is. That is why the timeline matters, not as drama, but as a foundation you can stand on. 3I Atlas was detected by Atlas, one of the survey systems built to notice motion against the fixed star field. The widely reported discovery date is July 1, 25. After that first flag, the global response begins. Follow-up telescopes take images, measure positions against reference stars, and submit astrometry. As the data accumulate, the orbit tightens. Predictive uncertainty shrinks. What looked like a change in course becomes what it usually is: the difference between an early orbit solution and a mature one. In orbital language, interstellar means unbound. The path around the Sun is a hyperbola, not an ellipse. An ellipse closes, a hyperbola doesn't. It enters, swings past, and exits, carrying its history back into the dark between stars. Initial characterization work describes just how unbound this visitor is. An orbital eccentricity around 6.1, a perihelion distance around 1.36 AO, an inclination near 175 degrees, and a hyperbolic excess speed around 58 kilometers per second. 58 kilometers per second is not a cinematic sprint. It is a steady, indifferent velocity. An object that did not grow up in the slow, near-circular habits of our solar family. And still, none of that implies anything artificial. Rocks can be fast. Ice can be ancient. Planetary systems scatter debris like sparks. The Milky Way is full of star systems that build comets and then lose them, flung outward by encounters and migrations. Interstellar space is not empty. It's a thin fog of leftovers, most of it too small and too dark for us to ever notice. Occasionally, A larger fragment passes close enough to betray itself to our surveys, and we call it a visitor. What makes 3 Atlas feel charged is not only that it is rare, only the third confirmed interstellar object we have tracked in detail, after Oumuamua and Twy Borisov, but that it arrives at a moment when we are culturally primed to treat any unknown as a message. And here the story deepens, because Comet is not a dismissal. A comet is a natural machine complex enough to imitate intention. A comet is not a single solid you simply photograph. It is a nucleus, often kilometers across, wrapped in an atmosphere it builds out of sunlight. As it warms, ices sublimate. Gas streams off the surface and drags dust with it. That expanding cloud is the coma, and the coma is what makes a comet visible from far away. It is also what makes the nucleus hard to measure, because the light you detect is mostly dust scattering sunlight, not the solid body itself. Even with powerful telescopes, you infer size from brightness and assumptions about albedo, how reflective the surface is. Then watch those inferences shift as the coma evolves. Phase angle matters too. The geometry between sun, comet, and observer can brighten dust through forward scattering, creating surges that look dramatic without implying any change in the nucleus. A comet can appear to wake up simply because our viewing angle becomes more favorable. High-resolution observations also show something crucial. 3A Atlas behaves like a comet in the way a comet should. Hubble observations described it as clearly active at about 3.80 pre-perihelion, showing dust emission from the sun-facing side of the nucleus and a weak tail swept away by radiation pressure. That is the language of a natural object, responding to sunlight. But morphology is where the internet tends to attach meaning, because tails and jets feel directional, like arrows. The tail is not a rigid pointer. It is a fluid structure shaped by forces you cannot see. Dust responds to sunlight like a continuous push, called radiation pressure. Ions respond to the solar wind like a ribbon caught in a stream of charged particles. The dust tail carries memory, curving and lagging, sorting grains by size. The ion tail reacts faster, snapping, and keying with invisible space weather. And all of it is projected onto a flat sky, interpreted by software, and then reinterpreted by a human brain that wants simple geometry. Change the geometry. Earth moves, the comet moves, the sun remains fixed, and the same physical structure can look as if it. A feature can appear sunward, producing what observers call an anti-tail, often explained by perspective when dust lies along the orbital plane. Comets can look wrong without being wrong. And comets can also move wrong. Not because they are steering, but because outgassing is a force. When gas leaves the nucleus, it carries momentum. If the outflow is not perfectly symmetric, if it vents more strongly from one hemisphere or through localized jets, then the nucleus feels a reaction force. Gas outflow speeds can be hundreds of meters per second to around a kilometer per second, easily enough to loft dust and to produce small but measurable recoil over time. That recoil accumulates into something orbit computers must account for. Over days and weeks, a tiny continuous push can shift the comet's observed position enough to show up as residuals when you fit the orbit. Residuals are not an embarrassment. Residuals are the place where a model admits that reality has texture. The simplest way to feel the comet's engine, if you want to call it that, is to remember how brutally the sun's influence changes with distance. Light and heat drop with the square of distance. At 1:0, you get the full solar input. At 2:0, you get a quarter. At 4:0, you get 1/16. So as an interstellar comet moves inward, the difference in heating is not subtle. A body that looked quiet far out can become active closer in, not because it decided to, but because different ices cross sublimation thresholds, because fractures open, because dust mantles fail, and because a coma can become dense enough for our instruments to measure cleanly. This is also why orbit determination is a living process. Each new astrometric point is a vote, and the orbit you publish is the compromise that best fits all the votes. Residuals, the tiny differences between where the model says the comet should be and where it is actually measured, are the whispers that tell you what you forgot to include. Sometimes it's a calibration issue. Sometimes it's a background star hiding inside the coma. Sometimes it's a non-gravitational push from outgassing that depends on rotation, sunlight, and the opening and closing of vents. And if you've ever wondered why scientists sound cautious even when they're excited, it's because this is the moment when excitement is most dangerous. A good model can be wrong in a way that feels convincing. A weak reduction can be wrong in a way that feels thrilling. The universe doesn't reward thrill. It rewards consistency. If you want to be rigorous, you don't argue about what the object is. You ask how the residuals behave as distance changes, and whether they correlate with changes in activity. To do that, you need to understand what the world's telescopes actually measure, because a viral image is usually a process product of many choices. Astronomy is less seeing than counting. Counting photons, counting positions, counting how brightness changes with time and wavelength. The observational web is layered, almost like an ecosystem. At the wide end are survey telescopes, fast, tireless, scanning for motion. They discover by coverage, not by depth. Their images are often shallow snapshots, enough to notice a moving dot. Then comes precision astrometry. This is where astronomy becomes a discipline of small differences, measuring the object's centroid against reference stars, correcting for distortion, timing, atmospheric refraction, and even subtle star catalog biases. If you want an orbit, this is the craft that builds it. Time series photometry adds another dimension, repeated brightness measurements that can reveal rotation, jet modulation, and outbursts. But photometry is not a single number. It is a measurement with a personality. Aperture size, background subtraction, filter bandpass, sky transparency. Each decision bends the reported brightness slightly. That is why two honest observers can publish different magnitudes on the same night. Spectroscopy is where the comet becomes chemical. Light is spread into a rainbow of wavelengths, and the coma's emissions add lines and bands. In classic comets, different molecules light up at different distances, some driven by water closer in, others by more volatile species farther out. But spectroscopy also carries its own illusions. Faint background stars, telluric absorption, instrument response curves that must be calibrated with care. And then there are the giants, the tools that feel like their own characters in this story. Space telescopes provide stability. Large ground-based telescopes provide sheer photon collecting power. Radio facilities provide a completely different kind of scrutiny. You can speak about Hubble, about infrared observatories like WST, about submillimeter arrays like ALMA, about Subaru and Gemini-class facilities. Not as magic, but as specific machines that answer specific questions. They do not decide what 3E Atlas is. They simply narrow the space of what it can be. But every channel has a trap. A faint background star can contaminate a coma measurement. A tracking error can stretch a feature into a jet. A subtraction pipeline can carve structure into noise. Even the simple choice of whether you track the comet or track the stars changes the appearance of everything in the frame. In one mode, the comet is sharp and the stars streak. In the other, the stars are sharp and the comet streaks. This is why processed images can be emotionally persuasive and scientifically fragile at the same time. That is why the only honest posture is an audit mindset. Every striking claim must map to a measurement channel, and every measurement channel must carry its uncertainty bars. Now we can touch the layer that made this a story, without treating it as proof. Speculation tends to ignite around a familiar set of tensions. Non-gravitational acceleration terms that seem larger than expected, tail or jet geometry that looks offset, sudden brightening episodes, photometry that seems inconsistent across observers. The disciplined way to handle each is to turn the tension into a question the sky can answer. If a model needs non-gravitational terms, how do those terms scale with heliocentric distance? Do they grow as the comet warms and fades as it cools? Do they align with moments when the coma becomes brighter or more structured? If the tail seems misaligned, what was the viewing geometry? Was Earth crossing the orbital plane? Did the object sit in a crowded star field? Was the image aligned and stacked correctly? Are multiple observers using different instruments? seeing the same morphology? If the comet brightens quickly, is it an outburst, dust mantle shedding, fragmentation, a new vent opening? Or is it photometric mismatch, different filters and apertures measuring different parts of the coma? None of these questions require you to be cynical. They require you to be careful. And because our era has learned to look for signals, some groups ask the most falsifiable question of all. Is it transmitting? Astronomers associated with Breakthrough Listen used the Green Bank telescope to search for narrowband radio technosignatures from 3 Atlas. Public reporting on their result describes an emptiness that is scientifically valuable. No evidence of technological radio signals, with claimed sensitivity down to around 1/10 of a watt in the frequencies they searched. Well below the power of a typical cell phone. If you are looking for a clear, testable boundary between interesting and engineered, this is one of the cleanest lines we know how to draw. So far, it hasn't been crossed. That matters. Not because it settles every possibility, but because it strengthens a pattern. Across channels, the object behaves like a comet, and it is quiet like a comet. So why does the story keep pulling at us? Because humans do not only respond to data, we respond to contrast. NASA speaks plainly. Comet, no threat, far away. The CIA responds with a formula that refuses to satisfy curiosity. And we do what we have always done under unfamiliar skies. We fill gaps. This is where the ladder of explanations becomes essential, not just as science, but as emotional self-defense. The first rung is standard comet physics: volatile sublimation, dust coma, jets shaped by rotation and sunlight, and occasional outbursts from fragmentation or mantle shedding. On this rung, a thrust-like effect is outgassing recoil, and an odd tail is geometry plus plasma data. The second rung allows the comet to be genuinely unusual while still natural. A fractured, porous body that vents in pulses. Unusual volatile ratios that activate at distances where most comets are faint. Fluffy dust aggregates that respond to radiation pressure in non-intuitive ways. Thermal lag that shifts activity away from the subsolar point. Rotation states that evolve as jets torque the nucleus, changing the pattern over weeks. On this rung, the question is not, what do we hope? But what model fits? The third rung is the speculative boundary, and it has a rule. You do not use it to conclude, you use it to define tests. If there were engineered propulsion, you would look for an acceleration profile that does not track solar heating, thrust that stays constant with distance, or turns on when sunlight is weak, or aligns with a fixed axis independent of rotation. You would look for emissions that cannot be mapped to known chemistry. You would look for repeatable narrowband signals that persist through independent observations. And you would commit, in advance, to what would disconfirm it. Activity and acceleration that scale with distance like sublimation, chemistry that looks cometary, and silence in signal searches where a transmitter would be expected to stand out. This is open-mindedness with guardrails. The door is not locked, but the evidence still needs to knock. And then gently, we return to the bureaucratic silence that opened the story, because it is part of the human landscape around 3 Atlas. A neither confirm nor deny answer can be nothing more than a policy reflex. It can also be a way to avoid telling the world what an agency pays attention to. In either case, it is not an astrophysical measurement. It is a statement about what an institution chooses to reveal, not about what the comet is. If you want to be emotionally honest, you can admit the feeling it creates, a classified shadow. But if you want to be scientifically honest, you have to set that feeling down beside the data, not on top of it. The sky does not care what we classify. It continues moving. Which brings us to what comes next, because in astronomy, the future is not prophecy. It is geometry. As 3I Atlas travels onward, viewing angles change. Phase angle changes the way dust reflects sunlight, and therefore the brightness we measure. Earth's motion changes our line of sight, sometimes flattening tail structures, sometimes revealing them. Heliocentric distance changes the energy budget, turning different volatiles on and off as the comet cools or warms. And each of those changes turns into a prediction you can write down in advance. How the light curve should evolve, how the coma should expand or fade, how the tail should respond to solar wind, how the residuals should behave if outgassing is the driver. There are also regions of the solar system that act like natural stress tests. Jupiter, massive and magnetized, dominates the dynamics of small bodies in its domain and sculpts plasma environments that can sharpen the behavior of ion tails. Even without a dramatic close pass, changing gravitational and space weather regimes can make models more diagnostic. If predictions hold, the comet looks ordinary. If they fail, the failure tells you where your physics is incomplete. And sometimes, a future window arrives with a surprise witness. Europa Clipper, on its way toward Jupiter, captured an image of 3E Atlas on November 6, 2025, from about 164 million kilometers away. Reporting in early January 2026 describes the observation as a 7-hour sequence taken by the spacecraft's ultraviolet spectrograph and stacked into a visible image. This matters because it shows the object is not just a social media echo. It is a target of opportunity for real instruments. Another angle, another wavelength, another way to test what we think we are seeing. It also hints at a new era of interstellar object monitoring, not only Earth's telescopes, but spacecraft scattered through the solar system, each with its own perspective, each capable of catching a faint traveler as it crosses their line of sight. And that, finally, is the emotional thesis of the whole story. When the sky is quiet, humans listen harder. Sometimes we listen so hard that we mistake bureaucracy for revelation. But the universe does not owe us immediate clarity. It offers signals, photons, spectra, trajectories, if we stay patient enough to read them properly. 3 Atlas, whether perfectly ordinary or subtly strange, expands our sample size. It reminds us that the solar system is not a closed box. Rare visitors cross through, stress testing our models, enlarging the edges of what we can explain. And for now, the cleanest pattern we have is not scandal but discipline, a cometary body, far away, behaving as sunlight and plasma would suggest, and silent in radio where a transmitter would have spoken. Somewhere out there, a small nucleus wrapped in a temporary atmosphere of its own making continues outward into interstellar night. It will leave us with data sets, not certainties, with residuals, not revelations. And that is not a disappointment. That is science doing what it does best, separating mystery from myth, one measurement at a time. If you want to follow the next windows as they arrive, with calm, careful curiosity, subscribe for more cosmic documentaries on Beyond the Solar Veil. Because the story is not in the folder that may or may not exist. The story is in the orbit we can calculate, the light we can measure, and the humility required to admit that sometimes the answer is still in transit.